While you sleep, an AI agent opens your training script, rewrites a section of the code, launches a 5-minute training run, checks the validation loss, and decides whether to keep the change or revert it. It does it again and again. By morning, it's run 100 experiments, and the model is better than when you left it. This isn't science fiction. It's Autoresearch, an open-source framework released by Andrej Karpathy in March 2026. The GitHub repo is public. The code is about 600 lines, and the results are real. In this video, I'm going to show you exactly how it works, the architecture, the math, the optimizer that makes it possible, and real benchmark numbers from actual deployments. Let's get into it. To understand why Autoresearch matters, you need to understand what ML research looked like before it. Training a language model requires an engineering team to manually design neural architectures, tune hyperparameters through exhaustive grid searches, watch training runs, read loss curves, make a judgment call, and start over. It's slow, it's expensive, and it's bottlenecked by the number of hours a human can stare at a terminal. Standard AutoML tools tried to automate some of this, but they operate on a narrow slice of the problem. They can't rewrite the model itself. Autoresearch does something fundamentally different. The agent doesn't tune parameters around a fixed codebase. It rewrites the codebase. It can change the attention mechanism, swap the optimizer, restructure the entire training loop. Anything, as long as the code compiles and the model improves. The entire framework runs on 3 files. This isn't a coincidence. It's a deliberate security boundary. The first file is prepare.py. This is immutable. It handles data loading, tokenization, and the evaluation harness, a function called evaluate_bpb, which measures validation bits per byte. The agent cannot touch this file. If it could, it would just hard code a perfect score. Locking the eval file prevents reward hacking. The second file is train.py, roughly 630 lines. This is the agent's sandbox. It contains the full model architecture, the optimizer, and the training loop. The agent has complete freedom to rewrite anything inside it. The third file is program.md, written by the human. It's the research agenda, what to optimize, what complexity is acceptable, and what failure modes to discard. Karpathy described it as programming the research organization in Markdown. The quality of this document determines the quality of the overnight run. The engine of Autoresearch is what Karpathy calls the Ratchet Loop. It works like a mechanical ratchet. It can only move in one direction. Every iteration either improves the model or gets reverted. The cycle runs like this. The agent reads program.md to understand the current objective. It reads train.py and a results ledger called results.tsv to understand what's been tried. It formulates a hypothesis, makes the code change, commits it to a Git branch, and launches the training run with a strict 5-minute wall clock budget. If the run crashes, the agent reads the last 50 lines of the log and decides whether to patch or discard. If the run completes, it extracts the val_bpb score with a grep command, compares it to the previous baseline, and either keeps the commit or executes a git reset. The agent never pauses to ask for permission. It runs continuously, hundreds of experiments sequentially, and the human wakes up to a results.tsv file documenting every decision made and a codebase that is measurably better. The 5-minute training budget only works if the optimizer is extraordinarily efficient. This is where Muon comes in. Muon stands for momentum orthogonalized by Newton-Schultz. The weight matrices in transformer attention layers, the query, key, and value projections, frequently have very high condition numbers. That means the variance is concentrated in a few dominant directions, and standard optimizers like AdamW update heavily along those dominant directions while ignoring the low-magnitude dimensions, even though those rare directions often carry critical learning signals. Muon solves this by applying an orthogonalization step to the gradient update matrix using Newton-Schultz iteration, a numerically stable approximation that runs efficiently in float-16 precision. The optimizer takes equally scaled steps across all dimensions, not just the dominant ones. The benchmark impact is documented. On the NanoGPT speedrunning leaderboard, Muon achieved the target validation loss in under 90 seconds on an 8H100 cluster, a 35% improvement over a heavily tuned AdamW baseline. In one overnight Autoresearch run of roughly 700 experiments, the agent discovered that increasing Muon's beta 2 from 0.95 to 0.98 produced the single largest improvement of the entire run, a 0.001 drop in val_BPB, by smoothing gradient normalization enough to allow larger, stable update steps. Autoresearch needs an AI agent to actually run the loop. In the most well-documented case study, training a folklore LLM by researcher Thursday Vu, that agent was Mistral Vibe. Mistral Vibe is an open-source CLI agent powered by Mistral Medium 3.5, a 128 billion parameter model with a 256,000 token context window. It scans your file structure, reads your Git status, and maintains project-wide context across the entire codebase. The weights are released under a modified MIT license, and API access is priced at $1.50 per million input tokens. The critical feature for Autoresearch is auto-approve mode. In standard operation, agents pause before executing shell commands or overwriting files. Auto-approve bypasses those interrupts entirely, necessary for the loop to run without human intervention. In April 2026, Mistral extended this with remote cloud agents. The developer initiates the loop locally, then teleports the session to Mistral's cloud infrastructure. The agent continues running asynchronously. The developer can close their laptop and retrieve a finished pull request when the run completes. The numbers from actual deployments are worth examining closely because they are not marginal improvements. In the folklore case study, the agent ran 11 experiments overnight. The baseline model produced fractured, semantically incoherent text. After the optimization loop, the final model generated grammatically complete sentences with coherent narrative structure. At Shopify, engineers adapted the Autoresearch loop to optimize their Liquid template engine, the rendering system powering millions of storefronts. The agent produced 93 automated commits. The result, 53% faster parsing and 61% fewer memory allocations compared to the human-optimized baseline. In GPU kernel optimization, researchers used the framework to tune CUDA kernels with throughput as the immutable metric. Starting from 18 teraflops, the agent landed at 187 teraflops, a tenfold increase with zero human intervention. In prompt engineering, a researcher treated a text prompt file as the mutable sandbox and used Claude's Vision API as the immutable evaluator, grading image outputs against 4 binary criteria. Starting from 32 out of 40, the agent reached a perfect score in exactly 12 minutes across 6 iterations. These results have accelerated a cultural shift in how the engineering industry thinks about AI-assisted development. Karpathy coined the term vibe coding in early 2025 to describe giving AI full control and forgetting the code exists. By February 2026, he publicly retired the phrase. The replacement framework is Agentic Engineering, documented by Google engineer Adi Osmani. It has 4 non-negotiable pillars. First, specifications precede prompts. You write comprehensive design documents before the agent touches the code base. Second, rigorous human review. Agent-generated code is treated with the same skepticism as code from a junior developer. Third, test-driven feedback loops. Automated test suites define the hard boundaries the agent operates within. Fourth, absolute human system ownership. Engineers retain deep understanding of what the system does and why. Autoresearch is the clearest working implementation of all 4 pillars simultaneously. The program.md is the spec. The val_BPB metric and immutable prepare.py are the test suite. The results.tsv ledger gives the human complete audit visibility. And the Git ratchet ensures only mathematically proven improvements survive. The Autoresearch repository is live at github.com/Karpathy/Autoresearch. The dependencies are minimal: Python, UV for package management, and a single GPU. The framework is explicitly designed to run on consumer hardware. For Apple Silicon, there is a community port using the MLX framework at github.com/Trevin-creator/autoresearch-MLX. The practical starting point is to clone the repo, write your program.md research agenda, and run it with Mistral Vibe or any MCP-compatible agent in auto-approve mode. What is significant about this framework is not just the benchmark numbers. It is the architecture pattern itself, an immutable evaluation metric, a mutable implementation sandbox, and a deterministic version control ratchet. Those three elements generalize to almost any optimization problem: model training, template engines, GPU kernels, prompt engineering, even sports analytics. The constraint is not the domain. It is whether you can define a single deterministic metric that the agent cannot fake. That is the insight, and it is more durable than any specific result. All repos, the Muon optimizer write-up, and the folklore dataset are linked in the description below.